So what we see here, we see a power system. Let me explain the power system diagram that we see on the screen first. Then I'll go and check with the statement of the problem what is written and what is required to be answered. So we have a generator here. We have the generator G, only one generator. Its capacity is 10 MVA. It's labeled as G, and then the generator is star connected, grounded through this resistance Rn. N is for neutral, 2.6 ohm, and it's connected through a 6.6 kV line to the transformer T1 of capacity 10 MVA, and it's connected in delta, and star side is grounded solidly, and then it goes to an 88 kilovolt line to a transformer, and as you can see is different from the transformer T1. It's labeled as T2. The transformer is labeled as T2. So can anyone tell me what is the difference between these two transformers that you see on the screen? Think about it in terms of whatever you find in terms of difference. Tell me the difference between the transformer T1 and this transformer is T1, this transformer is T2. I need to hear from you what you see in terms of difference between these two transformer T1 and T2. Say something. You have to say something, otherwise I will not be able to continue. Whatever you see in terms of a difference, just let us know.
Sorry, sir, is that a 3-winding transformer?
Yes, it's a 3-winding transformer. That's the correct answer. Anyone else? Any difference? Whatever you see on the diagram, or whatever you can think of it, let us know.
So there's also 3 different configurations for each winding. One's delta, the other is star solidly grounded, and the other is star solidly grounded with a resistance.
Okay, there is a little mistake in that statement. The third one you said solidly grounded with resistance is not correct technically. When you say solidly grounded, means the resistance is 0. When it is grounded through resistance, it's not solidly grounded through resistance, it's grounded through resistance. Is that clear?
Yes, I understand now.
So everyone must make note of that. When you're saying solidly grounded, meaning the resistance, if it is there, it is negligible, 0. When it's grounded through resistance, it's grounded through resistance. The word solidly will not be there. So that's correct. We're looking at the configuration. One winding is connected in delta, the other winding is connected in star solidly grounded, the other winding is star grounded to a resistance Rn of 4 ohm. And then we go to the line that is operating at 11 kilovolt, and then there is a fault point F. And if we come back to this 3-winding transformer, that is the correct that Sahil said, that is a 3-winding transformer. Normally, so far, I'm not sure, have you worked or have you heard of that 3-winding transformer before this? Anyone heard of 3-winding transformer before this? Anyone heard of 3-winding transformer before this?
Sir, is it the one they use in a cascade generator?
Cascade? What? Say it clearly.
Cascade generator.
The generator. Can you say it a little bit more? What
Yes, sir.
Say it more. Say more.
Cascade generator.
What is that cascade generator?
So when they connect a transformer like this to another one, so, and the voltage is becomes 2 times the output of the second winding.
Okay. Meaning they are adding them together.
Yes, something like that.
Okay. Any other thing? So these 3 winding transformers are used for various reasons. We can supply more reactive power because reactive power is a demand in the system. As we have demand of active power in the system for our resistive loads, we also have demand for reactive power in the system, meaning for those inductive loads. That also transformer is an inductive load, motor inductive load, induction furnace inductive load, and so on. So we need more reactive power. So when we need more reactive power, we can supply using 3-winding transformer. And also there is another application that if the transformer rating is very, very high, we can go with the tertiary winding. There is another application that when you need to reduce the impedance of the transformer circuit in cases where you need to reduce the fault current to such a level that it can go to the ground. So there are various applications of 3-winding transformers, and 3 windings are named as you see the letter P is for primary, S is for secondary, and T is for tertiary. So what we see, we have primary winding star connected, solidly grounded, secondary winding star connected, grounded to a resistance of 4 ohm, and tertiary winding is delta connected. Now there is another question that comes in here, is machine theory. It's not power system, but I am okay with spending few minutes here. You see 2 windings are star connected, but if we go back to the transformer T1, we see that one of the windings is star connected, the other one is delta connected. So you will see in most of the cases when you see them or when you design them, you will have in a 2-winding transformer, one of the winding is delta at least. Have you noticed that somehow, that if you have a transformer, 2-winding transformer, one of the winding is designed as delta or configured as delta? Did you notice that? Always, doesn't matter which side, high voltage side or low voltage side, but why high voltage side or why low voltage side, we can come to that. But did you notice that these 2-winding transformers always have a delta in it, or in most of the cases in it? We can have some transformer star 2-winding transformer star as well, but that is also a very special application, special requirement. Have you noticed that there is always a delta?
So for most of the cases I've seen, yeah, they are different. But why is that?
Because there are reasons. First one is, why do we have to have a star? If we think of star, we'll go to the delta. Why do you want to design your one winding, one side, high voltage side or secondary, primary, whatever you call it, one side is going to be connected in star? Why would you want that to be in star? You know the answer. You just need to tell me. Tell me. Every one of you actually know why would you want the three phases of the transformer to be connected in star? Why would you want them to be connected in star? You know the answer.
So does it have to do with the line currents and the
Not the current.
the voltage?
Yes, we will get.
The voltage is reduced by √3.
No, it's not about reduction. It will be reduced by the term 1 over √3. But the first point is just little different as compared to what you said.
Or is it because we can get a single phase circuit from it?
Yes, that's the point. We'll get two different voltage levels, meaning we'll get line voltage, we'll get phase voltage. If I have 400, then we'll get 230 as well. So we need that kind of thing. Three-phase voltage, we'll get single-phase voltage as well. That is what we need at some applications or in many applications. So when you need that or you want that, then you must have to have star, because if you connect that one three phases in delta, you will not get those two voltages different. In delta, what will happen? The line voltage and phase voltage,
They equal, sir.
they will be the same. So I have no option to get two different voltage levels. It doesn't matter with the magnitude. So if I need two different voltage levels, line voltage and phase voltage, whatever you call it, the words doesn't matter, but two different voltage levels are only achievable from the star side, not from the delta side. So if I need that, like for distribution transformers, from where our households are connected, or our offices are connected, or our commercial buildings are connected, are coming from the star side, right? So other side is delta. Why other side is delta? We know that harmonic that you asked at some point of time. I did not answer that question. I still remember harmonics and also the quality, power quality and issues, things like that. I'll come with that one because I'm lagging a little bit in terms of my content covering so far in comparing to the time that we have already spent. But it's okay, I'll come to that one. So harmonic is what we work with, the fundamental frequency of 50 hertz in South Africa. In some other countries, it is 60 hertz. That's the fundamental frequency. So that is what we want actually, 50 hertz. And that 50 hertz wave, if we could generate mathematically, like we can do it in MATLAB or other software, plot it, a sine curve, very nice, smooth, perfect. But in real life with generators, it doesn't happen smooth like the way we draw it in our softwares or other techniques. It is always stepped. It looks like a sine wave, but the increment is a step. Always, if we zoom in, and then we'll see that it's always step. And that step comes into the scenario because when the magnetic field of the generator moves from one location to the other, next location, that will cause the voltage to be induced in the generator stator windings, and that change of the rotor position from position 1 to position 2 is actually a step, because we cannot generate or design a smooth transition, because even if you make it small, still that smallest part is a step. Does it make sense?
Yes, sir.
Let's say I give you 10 rand. Now I want to increase it to 12 rand. So it's a step change, 10 to 12 step. You can draw that and visualize in your imagination that It's increasing from 10 to 12, it's steps. If you draw it graphically, you get a step change from 10 to 12. The increment value was 2. Now if you reduce that 12 to, let's say, 10 to 10.1, 10 to 10.1 is also a step change. That value, increased value is 0.1. Now you reduce it like what we do in integral calculus. We reduce the difference between two steps to a value which is smaller than the smallest possible difference that we can imagine. It's smaller than the smallest possible difference that we can imagine. Still, it will be a step. No matter how many, like you can say, like I said, 10.1. Now you can say, why 10.0? Why not 10.01? Why not 10.001? Why not 10.00001? Still, it's a step. So actually what we get in our physical generators, we don't get a smooth, perfect, ideal sine wave. We get a sine wave that looks like a sine wave, but it consists of steps. In each and every step, the rotor winding or the magnetic field changes its position from one to the other. Right, and that is now not a perfect sine wave. If it was a perfect sine wave, and if we analyzed that sine wave using Fourier transformation that you learned in mathematics, if you used Fourier transformation from a pure sine wave, pure mathematical sine wave, sine omega t, then we will see that it has only one component of frequency in it, which is the fundamental component of the frequency, 50 Hz only, or 60 Hz only, or 30 Hz only. But in our real life, we cannot have that. We always have steps in it. So if we analyze that one, what we will get there? We'll get multiples of that fundamental frequency present in that waveform that we are getting from the generator output. That causes the harmonics. All those multiples are harmonics. So if we take the multiples, now fundamental is considered as multiple of 1. So 50 times 1, that's the fundamental. First harmonic, second harmonic, so 100 Hz. Third harmonic, multiple 3 multiplied by 3, you get 150 Hz. Multiplied by 4, you get 200 Hz, and so on. So we see 50, sorry, 100 Hz, 150, 200, 250, 300, and so on. All these are harmonics now. Fundamental and then harmonics. Fundamental and then harmonics. And then we divide those harmonics into two categories. The odd harmonics, even harmonics, the multiples that we are taking, 2, 3, 4, 5, 6, 7, 9, 11, 10, 12, whatever. They can be categorized as even or odd. So even harmonics, odd harmonics. Right? So 150 Hz is odd harmonics. Third harmonic is 450, ninth harmonic, odd harmonic, and things like that. Now if you analyze this again using Fourier transformation, if you have taken that ideal one, you will get all odd and even harmonics will be cancelled out. There will be no odd and even harmonics. We will get only the fundamental, but in real life we get them. Now the first harmonic or the fundamental one is the highest one. So if you consider the whole waveform is 100%, you will get, let's say, 99% of, we can also find out using Fourier transformation how much, not only which frequencies are present, we also can find out how much of each frequency is present in that waveform. So 99%, let's say 99% is coming from the fundamental, 0.2% is coming from the second harmonic, the third one will be less than that, so 0.15 is coming from third harmonic, 0.10 less for 200 Hz, fourth harmonic, fifth harmonic will be less. So as we increase the order of the higher harmonics, then the percentage will be reduced and reduced and reduced. So the first one is the highest one, fundamental is the highest one, second order, second harmonic is reduced, third harmonic is reduced, fourth harmonic is reduced, and so on. Again, there is another thing. If we do the Fourier transformation, we see that it's just an observation when we talk about the sine wave, the positive half and negative half. The negative half is actually a mirror image of the positive half. And because of that, even harmonics are mostly cancelled out. That can be proved by mathematical derivation using Fourier transformation. We did it in our undergraduate. I'm sure you also did that. And it's a very, very interesting mathematics and understanding and philosophy as well. So you can study that one. So even harmonics will be cancelled out, but odd harmonics don't want to get cancelled out much. And for the odd harmonics, the third harmonic is the highest one. If you remember that I said as we increase the order of harmonic, they get their magnitudes of the values gets reduced. So if we look at the odd harmonics, third harmonic is the one which is going to have the highest magnitude or highest percentage in that 100%. Will be flowing there. Third harmonic voltage, third harmonic current. We don't talk much about the voltage, but third harmonic current will be flowing. We will have to provide a path for the third harmonic current to flow. So for that, what we do, we put that delta winding to make a circular path for the third harmonic current to flow in it. That's why we must have a delta. I'm not sure if I could explain it properly, but the thing is that when we have this composite waveform, it's not a single waveform that we work with coming out of the generator of 50 Hertz. It's a composite waveform. It has many frequencies, multiple frequencies in it, and if we do the Fourier transformation, we will know what frequencies are present. We will also know how much of each frequency is contributing into that composite waveform, like 99% of fundamental frequency, 0.2%, that all others will make 1% together. So third harmonic component will cause a third harmonic current flowing in the circuit. For that, we will have to provide a path for the third harmonic current to flow, so that when the third harmonic current flows, it doesn't cause any other problem, like it causes overheating problem and many other problems. So we can discuss that in other flow. So we must have the delta connection for providing a path for the third harmonic current to flow. That's why we put the other winding in delta. But like I mentioned, we can also have a star-star connection in a two-winding transformer. That's a very specific application. That comes from another scenario. It's a practical scenario which you... did I talk about the vector grouping at some point of time?
I don't think so, sir.
Okay, I did not tell you. So I don't know why they don't put that part in second year machine or third year machine. It's not there in the content, but it's a very, very important aspect when we think of connecting two transformers in parallel or two generators in parallel, like you saw in the previous example that we have had two generators in parallel connected to a common bus bar, and we do connect transformers in parallel in real application like everyday's application. So when we have to connect two transformers in parallel, we need to make sure that there are certain conditions that we meet, and especially if it becomes three-phase transformer, it becomes more. The number of conditions that we have to meet becomes more. If we have a single phase transformer, we have to make sure that the frequency is same. One transformer is operating at 50 Hz, the other must operate at 50. If the transformer one is operating at 60 Hz, second transformer must also operate at 60 Hz. There are reasons, we can explain that one. The other thing, we must make sure that the secondary voltage where the transformer is connected in the common side, or if the common is on the primary side, then we'll have to make sure that the voltages are same on which side we are connecting them in parallel. We can connect them in parallel on the secondary side. We can also connect them in primary side. We can connect them in both sides. That's possible. So we need to make sure that the voltages are same if it's single phase. And when it's three phase, we need to also make sure that the phase sequence that we talked about during this component analysis, symmetrical component, symmetrical fault, that phase sequence matters. So when you have two three-phase transformers, one is ABC, the other one also ABC. So A must be connected to A, B must be connected to B, C must be connected to C, or in other notations R, Y, B. R must be connected to R, Y must be connected to Y, and B must be connected to B. Again, the voltages must be same. Now these voltages will come in terms of whether you have one transformer, secondary winding or primary winding connected in star or delta. That will also make the difference in voltage. So you can imagine one transformer, you have the secondary winding in delta, what is the voltage available at the lines? The other winding is connected in star, what is the voltage available at the lines of that star connection? So that one thing that you have to need to make sure. The second thing, the next thing that you have to make sure is that there is no phase difference. Although we have ensured that we connected R to R, Y to Y, B to B, we made ensure that the voltage is same, like 400 volt between the lines of a delta, 400 volts between the star of another transformer. But again, there is no phase difference. This is sine wave. If you shift one of the voltages by some angle, there will be a magnitude difference. If you draw a line, if you draw two sine waves separated by a certain angle and you look at any instant of time, you will find the difference between the two voltages because instantaneous. We get the instantaneous values of voltages from the sine waves. So those instantaneous differences between the two voltages will cause a circulating current between the transformers, which we don't want. We want the current to be supplied to the load side or the source side. It will come to the transformer, not in between the transformer. So that is also one other thing that we need to make sure. That the last thing that is I am coming is the vector grouping. Vector grouping, when we have star connection and delta connection, in the two winding transformers, what happens, the voltages are not only transformed, like we use transformers as we know for stepping up or stepping down the voltage from one side to the other. It not only does the stepping up or stepping down, it also in the process shifts the voltages by certain angle, either plus 30 degree or minus 30 degree. So when you go from a delta to star connection, you might find that the difference between the delta side voltage and star side voltage, there is a angular difference. And because of that, you cannot just go and connect anything to that shifted voltage to any other thing. That will cause a circulating current in between the two. Does it make sense? It doesn't make sense, let me know, then I can explain a little bit in short. Can you respond, please?
So vector grouping is done to prevent circulating currents from occurring.
Yeah.
What is it? Can you repeat that again?
Okay, let me, maybe it's not correct of what I'm saying, but I'm giving an example now. Let's say I have two transformer, two winding transformer, I'm talking, not a three winding transformer. Now I'm talking two transformers. One is delta, primary winding is connected. You understand in primary and secondary better. Let me consider that primary, secondary, but I personally, I don't consider primary, secondary. I will consider primary, secondary when I have already connected it. Before I connected the circuit to a system, I don't consider them primary, secondary. I consider them as high voltage and low voltage. There is a reason for that. So I have a transformer. Primary is transformer 1, primary is delta. Let me draw it so it will be easy. Let me draw it, or you will see something. Shapes. Do we have some delta? Yes, we have some delta. And we have some star somewhere. Why? I don't know. Okay, instead of drawing, let me just write it. So I am writing D for delta and Y for star. This is transformer number 1, and I have another transformer which has both the windings connected in star. Does it make sense now? Two transformers we have, and we want to connect them in parallel. Can we do that? without thinking anything? We cannot. The reason is that when the voltage from delta side to star side will be transformed, meaning stepping up or stepping down, is not going to only step up or step down. The voltage will be either changed by plus 30 degree or minus 30. I can't remember it now because it's not that straightforward, star or what. There are another level in that one. We call it Y or 1, call it 11 or 1, corresponding to the clock, like the clock that we put on our walls. The hands are there, minute, second, hour. So if we look on, if we think that 12 o'clock is the reference, so if we go to 1 o'clock, we get 30-degree difference between 12 o'clock and 1 o'clock. If we go to 11 o'clock, we get plus 30 difference. So if it is, it also needs to be mentioned here, if it is 11 or it is 1. So if it is 11, it is plus 30 degree. If it is 1, it is minus 30 degree or plus 30 degree. I need to just double check that one. So we will get, when we have dy connection, either 11 or 1, we'll get a 30-degree difference between the voltages phase angle. But if we come to this yy, because it's y on both sides, the difference will be 0 degree. So now I want to connect this secondary side, y side. I am happy, both the sides are y, but there is a phase difference between these two voltages. Their magnitude same, their frequency same, but they have a phase difference in the first place, 30 degree. And because of that, there will be difference in magnitude, instantaneous values that we can always check from the sine waves. Do we have a sine wave here? Something like that. I don't know. It's difficult to draw something here with this PowerPoint card. So if I, oh goodness me, it doesn't. Okay. So let me just use this one. Oh, it's not helping. Hit this control button. How does it work? Do I have to close it? Yeah. Okay, I got that. I don't use PowerPoint to draw anything. I use other softwares. Let me try this freeform. So if I use to say this is the sine wave, forgive me about this top like table mountain top on this sine wave is not right. It has to be sine wave. So this is the first one, and if I take the same one, so it's the same, but they are phase shifted. So if I put a line here, vertical line, to check what is the difference in magnitude of the voltages, always will be there. So if I shift that line from 0 degree to 360 degree, I will always see that there is a difference between the magnitudes of the two voltages. Then if we connect these two transformers in parallel, circulating currents will flow between the transformers depending on which voltage is higher at that point of time. Does that make sense now?
Yes, sir. But how do you fix that though? What do you do?
Yes. That is where we need to know the vector grouping. I will need 2 hours for that. So if you give me a time in the evening time, I can sit with that and tell you. It has to be a separate class. And it's so important. I can tell you, when I learned it, I never discussed these things in the industry when I was working, but very interesting. Someone was getting fired, an engineer. So he came to me. I was very young at that time, though. I never thought he would come to me because, you know, those engineers, they have this mindset. They don't come to young people to learn. So one day he came to me, do you know vector grouping? I said, yes, I know. Then he said, okay, can you teach me? I said, yes, I can, but can you tell me why do you need these things now? Because I know the reason, but why do you need it? Then he told me that there were some transformers that were operating fine, no problem, but all of a sudden the transformer had some problem, it tripped, and then we had to isolate the transformer and find out the faults. And as you have now disconnected, you have to reconnect it. And when you're reconnecting it, you need to again make sure that you maintain all those conditions starting from the phase sequence, ROIB connected to ROIB phase frequency, no problem. We know that it's going to be the same frequency 50 Hz, but again, the vector grouping is the major one. So you do that. So when I taught him, then he told me that if he could not do that, he would have lost his job. And transformers are very huge device equipment, and it's very expensive as well, like millions of rands, you can imagine, big transformer. So we cannot do that. We can fix it if we have 2 hours time. I can explain it. So you let me know when you have time. At least
sir.
1.5 hours.
So I have one more question.
Yes.
So is it rare to see a delta configuration on the secondary side if it's like for distribution?
It's not rare. We see them in transmission lines.
But I'm saying like at the receiving end, for example, in our homes.
No, the connections that we receive at our homes is always coming from star side.
So if those harmonics, like the third harmonic, if it were to flow through like our equipment and stuff, I'm assuming it would damage our.
Yeah, they damage. They cause overheating. Because with that harmonic portion, that course question that you asked, I answered only the harmonic part that is coming from fundamental. Then multiples are called harmonics. Then we get odd harmonic. Then we get even harmonic. If the waveform is ideal or perfect, then there will be no harmonic. Only fundamental component will be there, 50 Hz or 60 Hz, and it will be 100%. The others will be 0, 0, 0, 0. If you want to express them mathematically, but in our real life, we don't get them from generator because of the positions of the rotor or the magnetic field as they change from position 1 to position 2. It is always a step, no matter how small that step is. So we get a composite waveform, and then we get all the harmonics in it, but the fundamental one is the highest one, then the order is increased, but the magnitude of those harmonics will get reduced. But I did not explain the effects of those harmonics in a way that it should be. I will discuss that in another point of time. But it has effects. Harmonics will cause harmonic currents, and those harmonic currents will cause more power consumption and overheating and damaging the equipment. That can be said in a very simple manner.
Thank you very much, sir.
So yeah. Oh goodness me! I took 40 minutes for this. Okay, let me go back to the star-star connection. If instead of okay, let me not delete that. If I have a star-star transformer here instead of delta star and star-star, why I would need such a configuration star-star? Because I might have a condition where I have used transformers in the upstream. Like we see here, we have a transformer, there is another transformer, there is another transformer. That's what we do in our power system. Highest voltage at the generating station, after the transformer, then we step down. So a series of transformers are there actually in series. So when we have transformers in the upstream, we have already shifted the voltage by 30 degree plus minus. And by shifting, now I want to connect another one, but I cannot shift now anymore, because if I shift, then the voltages will be shifted, and then I won't be able to connect them in parallel. So I don't need any shift. So I will go for star-star 0 degree. With star-star, it's also possible to shift by 180 degree. It's not only 0 degree. That can be explained in that other class that I mentioned. So when I don't need any phase shift or cannot have any phase shift between the voltages from the primary side to secondary side of the transformer, I must choose YY0, and I can do that. by connecting the windings of the transformer in a particular way, and I have to know that as an engineer, because if I don't know, if I just go and connect them in star, that will be a disaster. And that's what we do in our practicals in the universities. Without knowing, we just go and connect them in delta, we just go and connect them in star without knowing. That's a disaster to me. I cannot do that. No one should do that. You cannot connect two batteries or put two batteries in your remote control of your television set, or you cannot just put your battery in your cell phone without knowing the polarity. Do we do that? We cannot do that. But those, luckily, the way they are designed or mentioned, or some labelings are there that we must insert, like for cell phone, it won't go in if we put the battery in wrong way, because it's also a mechanical protection. The designers also consider that someone might not know about anything about the polarity, plus, minus, anything at all. But I won't allow that person to insert the battery in a wrong way at all. You can break the battery or the cell phone, but it won't go in, because that wrong insertion will damage. Similarly, for the other example that I said, the remote control of the television set. For remote control, it's not that you cannot insert, you can insert, but the levels are there, plus, minus. Because it's done from the factory, it comes from the factory, and levels are there on the battery, on the remote control set as well. So that's the same thing comes into the transformer winding. Although it's AC, still it has polarity. I'm not sure again, in any module they talked about the winding polarities of an alternating current transformer winding, or a motor or a generator. They also have polarities. So when we connecting the transformers in series, when we connecting them in parallel, we need to make sure that the polarities are also considered. Okay, so that's that part. I'll discuss that thing in that extra class if you want. Oh, sorry. If you want, then we'll know more about that. How do we know the polarity? Because it's not written there. Unless it is written there. Sometimes we write them because we don't want to make that disaster. And it will be honestly a disaster, no doubt. Electricity doesn't forgive anyone. That thing we must know. So we can have different situations. So let's go back to the problem. The reactances of the generator transformers are shown there. So generator X1, X2 and X0. Transformer 1, X2 and X1, they are same with X0. Through reactances are same. For transformer 2, the reactances are given for each of the windings: primary winding, secondary winding, tertiary winding. So they are given here. So we'll use them. And notably, I'm not sure if any one of you have noticed that I kept this tutorial was a very typical one, difficult one, and it has many things in it. I initially wanted to avoid the reactance calculation like we did here. The question that you asked, that its own capacity, megawatt, and then the base MVA was different and all those things. So we had to do this calculation before we could go to this drawing of sequence network and fault calculation. So that part I just wanted to avoid here, because we did that calculation, we know it. If we learned it, we learned it. And then I kept the MVA ratings to be the same, 10 MVA. That was my intention. I kept it same because I want to avoid that calculation. If we want to learn that part, we can go back to that previous tutorial and learn how to get to that base value and convert them to that common base value. So that 10 MVA is for all of them. We don't need to convert anything here. Is that clear? Is that clear?
Yes, sir.
I saw some of you answered that chat facility was not, I did not click that one. So thank you to Nocholo, who said you want the neutral point, and because of that neutral point we get two different voltages. Thank you for that answer. It's also correct. So I wanted to avoid that part. Now we coming to the problem. It says the single line diagram is shown in the figure, and we have to consider a fault at F, single line to ground fault, right? So what it says, find out the phase current IAF in amperes, like in amperes we did in the previous one. Currents in each phase of the 88 kilovolt cable in 88 kilovolt cable, we have to find out the currents in each generator phase. Current is in currents in each generator phase, three-phase generator in amperes. Current in each neutral. This generator is grounded through the resistance. This generator transformer is grounded through the resistance, so we have to find out the neutral current as well, and their power consumption in the neutral resistance. Some currents will flow, the power will be consumed here, I square R, and we know that formula. So that's what we have to do, and you will do this part, repeating this part you will do for a line to line fault. So I'll do one, you will do the next one. So to start up with that one, what we do, I drew this diagram, so I will put it here so you can save some time. So let me just copy and paste that one. But we'll analyze it so that we understand exactly what we are talking about. So this is the positive sequence. I made it small, make it big. This is the positive sequence network. Because we don't have to do the reactance calculation, they are going to remain the same, because the base MVA, whatever we choose, in this case we will choose the base MVA as 10, and then we convert, so 10 MVA over 10 MVA and multiply it by the respective reactance, they will remain the same. We don't need to calculate. So we can go to, let me just write down that word for you. We can also say that let's say base MVA is 10. That is equal, if you remember that we are saying if we choose the base MVA wisely, then it will reduce our calculation. This is also an example of that. That is equal to the MVA rating of each of the equipment G equipment G transformer 1 and transformer T2. This reduces the calculation of the reactances. They remain the same. So you can make this note in your book. So coming to the positive sequence network, so this is the reference bus N1. We go show the voltage source, negative, positive with the polarities are shown here, and then we show the positive sequence reactance of the generator. I also wrote it here, J.15. The transformer reactance, positive sequence J.1, T1 is having J.1. I wrote it here, and then we go to the 3-winding transformer, and when you drawing the positive sequence network of the 3-winding transformer, the tertiary winding will not come into the scenario. It is only primary and secondary. Both will be shown here in series. We need to remember these few points. Tertiary winding reactance will not come into the scenario. Only primary and secondary reactances positive sequence will come into the scenario, but they will be in series. Is that clear to everyone? Let me know.
Sorry, can you repeat that?
When we are going to this tertiary winding transformer and drawing the positive sequence network, when we considering the 3-winding transformer, we going to the positive sequence network, the tertiary winding will not come into the scenario. Only the primary and secondary reactances will come into the scenario, and they will be in series. There are theories for that. We don't have to go there now because it will take another 2 hours or 1 hour. So I just want to keep it small to Remember it that way. Tertiary winding will not come into the scenario. Primary and secondary windings will be in series. That's what we did. X1P. X1P is the positive sequence reactance of the primary winding. X1S is the X1 positive sequence reactance of the secondary winding that are connected in series. And then we arrive at the fault point. And then we reduce it. All the reactances are in series, so we add them. 0.15, 0.1, 0.04, 0.03, that gives us 0.32. And the voltage source is also shown there.
Sorry, sir. So this is like a general rule.
Yeah.
You consider the positive sequence
It's not
network.
general rule, it comes from the theory.
Oh, so it's just the specific case. We don't worry about it.
Yeah, we may not worry about that now, but we may need to worry about later on in our real life. Like I gave you the example that that person came to me to know what is the vector grouping. So it can come back to us at say we don't know now. So for us, for now, we can say it that way. The tertiary winding will not be in the positive sequence network. Only primary and secondary will come into the scenario, and they will be in series. And then we reduce it. Okay. Is that clear?
Yes, sir. Thank you.
So let me go now to the negative sequence. Let me copy and paste it here. For the negative sequence one, again it's the same thing. The tertiary winding will not come into the scenario, only primary and secondary. So we start with the N2, reference bus, neutral bus, X2 of the generator, that is 0.1. We get it from this table. And then X2 of the transformer T1, X2 of the transformer T1 is 0.1. We wrote it here. Then X2 of the primary, we go there. X2 is equal to 0.04. We write it here. And then the X2 of the secondary is 0.03. So they are also again the same thing like the thing that we did in case of positive sequence network. It's the same way. Tertiary winding is not coming into the scenario, and we find all of them are in series between N2 and F2, and we add them, we get the value of 0.27. so that's the negative sequence network. So let me keep it there, positive sequence network and negative sequence network. Can reduce it a little bit. Yeah. So they are following the same principle, positive sequence network and negative sequence network. They don't consider the tertiary winding, the primary and secondary winding of the three winding transformer is coming into the scenario in series. So when we are done with that, we can go to the zero sequence network. So let me copy it. Let me make some space for the zero sequence network. I can delete this text as well. So for zero sequence network is coming from a different perspective now that I told you that I will show you with some example. So the tertiary winding is coming into the zero sequence network. So how we show it, we start with the primary side and then we have 4 switches if we remember. 1, 2, 3, 4, those 4 switches. 2 of them are in series, 2 of them are in parallel. So how we showed in the positive sequence and negative sequence, we showed them in series. That's how they were shown here. So we can come to this one now. They are shown in series, impedance of the primary winding, impedance of the secondary winding, they are in series. Now we have to consider the tertiary winding because it's zero sequence, and we also have to consider the switches and their connections. So how do we do it? We look at the general part first. This switch is going to be closed, this switch that you see here, because that tertiary winding is connected in delta. This tertiary winding is connected in delta. I have not shown this closed yet. I will show you the closed one in the original zero sequence one when it is going to be copied and pasted. So this is in delta, it will be closed, and this link is in between. This is going to be left open because we cannot have zero sequence current flowing in the delta connection that we have shown here for tertiary winding. We know that zero sequence current cannot flow, so we show it, although we don't need to show it. Like there are things that we remember, although we don't need to remember because it might have a different case in some other cases. So this link, you can forget about that. You can show just this one is perfect. So that's what we are going to do in the original or actual zero sequence network that I'm going to show now, how we have drawn that circuit. So we start with the neutral bus. Remember, start with the neutral bus, and then we have to consider the neutral of the generator. So 3 Rn, if you remember, the impedance of the neutral and ground is coming as multiplied by 3 times Rn is going to come here. We'll consider the value during the calculation time, and then the zero sequence reactance of the generator, and then we put a open here and look at the connection. So we will have to connect it, but one open is missing here because I intentionally dropped the open of the generator because it's not required, it's closed, it's star connected and grounded, so that is closed, that's not shown here. And then I come to the transformer. This is the transformer winding and it's delta, so this star connection that side cannot be connected or closed, it's left open, this delta connected, so the shunt is closed. We come to this 88 kV side, we see that it's star grounded, so that is closed, and shunt cannot be closed because it's star connected, it's not delta connected. So we're done with the transformer 1. Is that clear? Up to transformer 1, if it is clear, let me know. Is it clear, or do I need to explain it a little more?
So you said you intentionally left that switch open.
No, that one is for that. No, intentionally I showed it connected for the generator, because if you remember, for the generators what we were doing for zero sequence network, this is one. I need to show the zero sequence network. Yes, this zero sequence network, when I was considering the zero sequence network, I was always showing an open and then I will close it looking at the connection. Can you follow that? So XG1, generator 1, I show the reactance, then I leave it open, and then I go back and look at the connection of the 3 windings of the 3 phases. So I find that it's star connected but not grounded, so I cannot close it. But if I go to the second one, I left open here initially, and then I go there back, I see star connection is grounded, so I close it. You understand? But for this one, what I did, I closed it in the first place intentionally, and then I come with the transformer. This part is the transformer. Let me put a circle. Where is that fill thing? So this part is the transformer. The generator is already closed because it's star connected and grounded.
Oh, okay, I see, sir.
Yeah, so I avoided that open, showing an open, extra open, because it's already closed. I could see it from the diagram of the power system, star connected and grounded. So that opening is already closed, and this opening is 4 switches, 2 in series and 2 in parallel. So I look at the transformer connection delta, so shunt switch is closed, and this side is star connected grounded, so series switch is closed. Done with the transformer. Now we can go to the 3 winding transformer. It has primary, secondary, and it has star connected grounded resistance. So we put them in series. They are all in series. Primary reactance X0P, secondary reactance X0S, and then the neutral multiplied by 3 that is coming here. Now we need to show that in terms of the tertiary winding that will come from here, and that is that one, X0T of the transformer, sorry, tertiary winding, X0T of the tertiary winding, and this side is closed shunt switch because it's delta connected, and this one is shown on this side in series with the secondary reactance, not with the primary reactance, because this resistance is on the secondary side, not on the primary side. If the primary side has had a resistance to the ground, then we would have another resistance here. We could have possibly, because both the sides are grounded, star connected. So one side has resistance, so that resistance shown in the diagram is with that side. So it's on the secondary side, it's on the secondary side. If it was also on the primary side, it will come with X0P in series. Does it make sense? So this is the 3 winding transformer. So we see, look at the primary side, star connected grounded, so we close the series switch. We cannot do the parallel switch. Star grounded, this one is closed. This one here is closed. Star grounded to resistance, the resistance is coming multiplied by 3. Where it must go? Before this tertiary winding or after this tertiary winding, or we can think in another way, should it be in series with the primary winding or secondary winding? We just look at where the resistance is coming from. The resistance is coming from secondary side, so it should be in series with the secondary side. If it was coming also or from primary side, it would be in series with the primary side. Is that clear now?
Yes, sir.
Okay. Now we have all other values we don't need to calculate for reactances, but for the resistance 3Rn, that needs to be calculated. Can you calculate and tell me the value? One value is already written there, 0.992 for the transformer 2, but can you confirm that you can get that value? That 3Rn, you can see that I wrote it there as 0.992. Can you get that value and confirm that you are getting that value? It needs to be calculated. These two Rn values need to be calculated because they are in ohm, they are not in per unit. All other values there are in per unit. These two Rn values, one for generator, the other one is for the transformer T2, 3-winding transformer. So I have shown that value of Rn for the transformer 0.992. Can you calculate and tell me that you getting 0.992? It should not take more than a minute.
So I got the same answer.
Anyone else? I need to hear from many of you. Nokcholo, can you tell me that you got it? Zakari, whose names are there? Sibusiso, Mukundi, Mikash is there as well. Sinakonke is there. Saneliswe, Timira is there. Tell me the names, sorry, the value that you're getting, 0.992. That 3Rn value you need to calculate and tell me that you're getting 0.992. And when you got that one, we need to get to the 3Rn value for the G as well, generator G. So you will tell me the two values of 3Rn that you are getting. What is happening? It does not take a minute.
Sorry, so you want the other resistance value?
As well, I need both the 3Rn because we need.
I got the final value as in 3Rn equal to 1.791.
Yes. I need to hear it from others if they're getting it. So 3Rn for T1, I'm writing this way. T1 is 0.992 per unit now. It was not in per unit in the question. It was in ohm, 4.0 ohm, and 3Rn for the generator is how much? You said 1.790 per unit. We need to know it from others as well. We need to calculate these two at least because they were given in ohm, they were not given in per unit. If they were given in per unit, then it would have helped us. But this is very minimal calculation that we must be able to do.
Sorry, sir, can you just explain how you got the 0.992?
What is the way how you convert ohmic value to per unit? Tell me that. How you have some ohms, 2 ohm, how you convert that 2 ohm to per unit? What is the formula for that? You used it in power systems 1, we used it in this tutorial session yesterday or day before yesterday, or not day before yesterday exactly, last week. What is the formula that you use for converting ohmic value to per unit? Do you remember that? Or if you have that one, you can go back or you
I
can
think
ask.
it's actual over base.
Hmm?
Actual over the
Yeah,
base.
actual over base ohm, actual ohm by base ohm. But
Yes.
if we don't have base ohm, we can do it directly. It comes from the base as well, but we can do directly. I gave you the formula. The formula is X ohm times base MVA over kV squared, because it's related to both base MVA kV, and then you calculate that base value and you can go to that route. But I want to jump one step, and that's why I use the formula X in ohm multiplied by base MVA divided by kilovolt squared. Can you now find out and confirm that you're getting 0.992 for the first one, transformer T2? The voltages are different. The generator is operating at 6.6 kV, while the transformer T2 is at 11 kV. If you need to look at the system diagram, are you getting? I won't move until or unless you confirm it, at least one of you. Then others can copy and paste. At least one. Sahil said that, but I want to hear it from anyone of the remaining. Zakari got it, 99173, and that's good. And the 3RN4 generator as well. I need both the values that you are getting right, because they are operating at two different voltage levels. That needs to be observed from the diagram. It's not written in the question. That needs to be observed from the, what is that E2? Give me the value, Luto, final value for generator. And you forgot the part 3 times, because in zero sequence network, their resistance between the neutral and ground is always going to come multiplied by 3. It doesn't come 1.7 as Mikashmul. I thank you very much. 1.7906. So that's how we get those two resistance. We will need them because in the question they asked us to do the calculation current through neutral resistor, so we will need them. Also, we will need them to reduce this circuit, because if you remember, for positive sequence we did the reduction here, for negative sequence we did the reduction here. Now we are we are at the zero sequence network. We need to do the reduction, the reduced. Now you tell me the effective or equivalent resistance of this reduced diagram. Now you tell me the reduced network reactance values, if I can, or should I keep it still big so that you can see? Okay, let me make this one small. Then keep this one somewhere else. I can keep them here. And now we need to know, if I go and copy something from where I can copy it from. Let me. I need now the reduced diagram for this zero sequence network, because for positive and negative sequence we did it, and for this zero sequence network we have to do the reduction. Neutral bus, and this will be F0, and this is the equivalent X equivalent 0, and this is what we need to know. What is the X equivalent 0? Who can tell me that value? That is what we are looking for at the moment. You can say it. Luto got it. Thank you. Who can tell me the equivalent reactance of this zero sequence network that we have shown here? How do we do it? You know the process. You start from the fault point, you try to reach the neutral point, neutral pass, and in how many ways you can go there, and then take the combination of series and parallel connections. So you can start with F0, and then the first one is you can come this way, you cannot go. You can see there is an opening, you cannot go. So you can come this side, you see, yes, there is impedance, you can go in this way, you can go continue, reach the neutral, fine. Is there any other way? Yes, you can continue, come this way, in this way you cannot go. So that line is dropped, you can continue and then go this way, can you continue? No. Now you go this way, check this way, you can continue, go back to neutral. This way is the last one, open, so you cannot continue. So now we need to find out how they are connected. Draw it in your book. And tell me the final answer. Who got it? Remember one thing which is very important here in the zero sequence network. There are reactances, X values, there are R values, resistance as well. Don't mix them.
Sorry, sir. Could you explain the concept behind like the different parts leading to that bus?
Concept is if we can reach there or not. If there is any open, we cannot go that way. Simple. I start from F0. The first one I come across is this one. Can I follow this path? No, I'm broken here. I cannot go. Forget about that. So I go to this next one. I can see impedance, but I still can go. It's opposing reactance, impedance, it's impeding, but I still can go through if I have the enough force. Can go through. Come to this one. Yes, there is closing here because of the delta connection of the tertiary winding. I can go through, and this way straight, no impedance. So I can go through. So this is one line that you must draw. Like this, just like this, draw just like this, horizontal, this reactance is horizontal, this reactance in vertical combination, or the way you see it, if you don't understand, still just draw it just like that, and then you draw this horizontal line reaching the neutral bus. So that one is complete. Now I did follow this path already, so I come to this one. I continue pushing through the impedances. Can I go through this? No. So I leave it to up to this point. Then I can continue this side. Yes, I can continue closed. This one I can continue because it's closed. So I arrive at this point. Then I cannot continue this way. So I drop that. So can I continue this way? Yes, there is some reactance I'm pushing, and then I'm coming to this path. Yes, I can continue. I reach the neutral bus. So this is now complete, and the last one is this one is opening, so I cannot continue down. Now I come back and look at how the reactances and resistances are looking like, how they are connected, series, parallel, or how, and then we find the one value that will look like. It will be reactance and resistance. Although I wrote X equivalent, I will know the X first, then there will be R value as well, because you can see when I follow this path from F0, this is the resistance present here, it's not the reactance. So reactance is there, resistance is also there. This one is a very typical example that I told you that I put so much into it. So that's why I put the resistance as well. I could have put reactance in the generator neutral and star. Sorry, generator neutral and ground. I did not intentionally. So reactance is there, resistance is there in this zero sequence network. So we cannot add them directly because they are resistance and reactance. 0.55759 from Luto. No, that's wrong. Sorry about that. It's not close to the answer I have. Sabelo 0.992 plus J 0.67, that is the correct answer. So we can write it as JZ equivalent 0.992 plus J 0.0668. That's what I have. I'm writing it Z impedance because it has X, it has also R. So R plus JX, R is 0.992, that came from that 3Rn of the transformer T2, and the X came from the combinations. I need to hear it from you.
So I got the same answer.
That's great, thank you. And who else got this? Who else got this? Nikas? Nikas got the same. That's good. Thank you very much. Anyone else? Who got it? Who else got it? I just want to hear from one of you at least. Okay, 3 of you said, but I still want to hear it from one of you. This is very important. It's basic. Taking us back to the fundamentals that we have learned in some other modules. But it's very much applicable. It will always be like this for zero sequence networks. We have seen it in other tutorials. So this one is different, so I want to confirm that you're getting it. So if I can take this opportunity as you are still working on it. It's already 12:16, but I will still wait for 2 minutes, no problem. So it will have very high this one. How I draw a resistance there. Okay, let me put a text box and say R in it. That's much easier. Who got it? Tell me so that we can conclude this part, otherwise we cannot continue, because the next step will be the interconnection of sequence networks. I will do that in the next week. Tell me quickly. You cannot get it. Draw it the way I explained. You start from the fault point, check which path you can follow to reach the neutral point, and then show those reactances present. If you cannot continue, then you can drop that one off, no problem. Keep the paths with the reactances that takes you to the neutral point. I'll stop it with this equivalent resistance for today. Just I want to know from one of you remaining before we close this session. Point 008. I have 0.00668. I don't want the path one, I want the equivalent one, complete. One value of reactance, one value of resistance. That's all we need. Okay, I'll give you 1 more minute, then we'll close, and next week we'll continue. But make sure that you try it at home. Cholo is lost. Can you follow before we close it? Can you follow? Look at the screen, what I'm doing. My mouse pointer is where? Can you tell me where my mouse pointer is?
At the fault.
Yes, so I'm starting from the fault and we'll try to reach the neutral bus in all the possible ways. So I come to this, it's closed, so I can follow and come to this way. The first one I come across, I can see that there is one opening, I cannot continue. So forget about that. So I go back to that common point where I arrived from fault point, starting from fault point, then I can see there is an impedance. It's closed path, but impedance will impede, but I can still go. So I go through. I arrived at the resistance. I can go through. It will resist, but I can go through. Then I arrive at this common point. Then I don't go that side now. This is the first one. So I see there is reactance. It will impede, but I still can go through because there is closing here. So I can reach the neutral path. Just draw it like this in your book. The way exactly it is on the diagram. If horizontal, vertical, the way you see it, just draw it just like that. They are in horizontal form, and there this is one in vertical form. Just draw it just like that.
So I did draw both the
Okay.
parts, but now I'm confused with combining like both. How do you
So
combine?
share your screen. Let me stop my sharing. Share your screen. Show me what you have. Or your computer, your phone, or whatever you are using. I don't know.
My like I can't share my screen, so I'm
Can you
at
show
the
it your from your camera? Just hold it in front of your camera.
LAN, so they don't have like the cameras on the
Oh,
PCs.
at the LAN you don't have it. So if you have it, so this is you can see you have drawn this one, right? You have drawn this one, and then we come to this X0P is going to be there, and then we cannot follow this path, right?
Please share your screen, sir.
Oh yeah, I stopped sharing because I thought you will scare. Okay, so that line was drawn with this reactance in series with the resistance, and then this one particle just like that, and then we arrived at this point. Then we can now go try this path with X0P. Yes, we can push through. It will impede, but we can push through, and then I try this path, not allowing, so it drop. So I can continue from this point. You see, close, close, continue, then come to this. Doesn't allow me. Opening is there, so I drop it off. I can continue this path. Impedance is going to stop me, but I'll push, and then I can go through this one. There is a close, so I arrive the neutral bus. So after that, I look at this option. That is the last one. There is opening. I cannot go through, so drop it. So what is happening? This is like this, and then this is going through like this. Now you look at the connections, how they are connected. They are going to be in like this. Let me show you what I have. What will happen? This circuit will look like this. Can you see? This one is giving this two in series, so you cannot do anything. But this one is connected here, and then we can come this side. Then this portion actually is in parallel with this one. Can you see? This portion is coming to neutral bus and is in parallel with this portion X0T. And X0T is 0.05, that's that one. And then these two in series, X0P and X0 of T1, they are in series. X0P is 0.4, X0 of T1 is 0.1, so 0.1 and 0.04, they are in series. Can you see that now?
Yes.
Okay. It should be clear to everyone now how they are coming in parallel. This portion is going to be in parallel with the series of these two, because that's how it is. So everyone is okay with this now?
Sir.
Okay, thank you very much. So we'll continue next week. We have to calculate the currents.